Alright, in this video, we study what addition and multiplication of complex number means in geometric terms. So let's start. First, addition. Okay, suppose we have two complex numbers, a plus ib and c plus id, let's say. And of course, a, b, c, d are all reals. And I is the imaginary unit. And as we have seen before, these complex numbers correspond to points in two-dimensional space, right? And if we add them, if we add these numbers, what we have is, so if we add these two, we have a plus c and I b plus d, which corresponds to the point a plus c and b plus d. So on the two-dimensional plane, complex plane, what does that mean? Okay, so let's draw a picture. So this is real axis and this is imaginary axis. And suppose, let's say, a plus ib is this point. So this corresponds to a, b. And suppose another point is here, c plus id. So this point on the complex plane, it corresponds to cd, right? So if we add this point to this point, what we have is this. So let's see. So 1, 2, and something like this. Okay, so this would be a plus c and b plus d. Okay, so that means we have this parallelogram. So this length and this length is the same, and this length and this length are the same. And of course, this edge and this edge are parallel to each other, and also this edge and this edge are parallel to each other. So the difference between, let's see. So this difference, okay, so this corresponds to C, and this difference corresponds to D, okay? Because this is C and this is D, right? So we just move this edge to this edge by translating in the parallel manner. Or alternatively, we can say that we move this edge to this edge. Okay, so connecting this source to the target of the other point. So in this way, we have addition. So addition, this point corresponds to this complex number. So addition corresponds to translation of points. So either this point is translated to this point or this point is translated to this point. But either way is fine because, as we have seen, addition is commutative, so the order doesn't matter. So it's simple. Next, we consider multiplication by a real number. So let's say c is real. And if we multiply the complex number a plus ib by a real number c, then what we have is ca plus icb. So what does this mean in on the complex plane? So let's draw a picture. So again, this is real and this is imaginary axis. And if we have this point, a plus ib, and if c is positive and greater than 1, so what this point means is an extension of this arrow to some point. So the point is ca plus icb. Okay, so this x coordinate or the real coordinate number, real part is C times A. Okay, so the ratio between this one and this one is C. And same for this one. So the ratio between this and this is C. So if this is 1, then this is C. Because, but this is actually B, so this is CB. And this is A, so this is CA. If C is negative, then it goes in the opposite direction, but it's just opposite, okay? But on the same line as the original arrow, this one. And if C is less than, the absolute value of C is less than 1, then this arrow shrinks, okay? But anyway, the ratio is still C. So C is the ratio of the length between this and the resulting arrow. So if we multiply by a real number, this is very simple to understand. But if we multiply by a complex number, then it's a little bit complicated. So next we consider that. But before considering multiplication by any complex number, we consider multiplication by a complex number of length 1. Length means absolute value of 1. Okay, we consider a complex number such that its modulus or absolute value is equal to 1. We consider this one first because any complex number, let's say z, can be decomposed into this way. So as long as it's not 0, it can be written as this, absolute value of z times z divided by the absolute value of z, because they cancel, right? And this part has the absolute value of 1. So it's easy to see, because if we take the absolute value of this complex number, it becomes absolute value divided by the absolute value, which is 1. So any multiplication by some complex number can be decomposed into two operations. First, we multiply by a real number that is positive, and then we multiply by a complex number whose absolute value is 1. So this one, multiplication by real number, has been considered here. So now we consider multiplication by this complex number. Okay, first I will show you what would happen if we multiply any complex number z by another complex number u, where the absolute value of u is 1. Okay, the absolute value of z we don't care. Okay, so again on the complex plane, if we have complex number u and the length of this arrow is 1, of course the length means the absolute value of u, and another complex number z, if we multiply these two complex numbers, what we have is something like this. And that means, let's say this angle, argument of u is this, then this argument, this angle here is same as argument of u. Okay, and the length of this new complex number is the same as the length of z, because it's easy to see. The absolute value of z is, so absolute value of a product is the product of absolute values. And we have seen this before. And this one is u. U is 1. So the length doesn't change. But the angle changes. And this angle is the same as argument of u, the principal argument of u. So the effect of multiplying by u is to rotate this z by the argument of u in the counterclockwise way. Counterclockwise, so this direction, not opposite direction, not this way, clockwise, but counterclockwise. So that's what would happen. So this is, let's state this as a theorem, okay, and then we will prove it. Okay, now let's prove this in steps. Step 1. First, consider the complex number 1, okay? So this is actually real, but anyway, if we plot this and imaginary, and let's say 1 is here, okay? This is a complex number. And if we multiply by any complex number u with unit absolute value, then u times 1 is equal to u, of course. So if we have u here, okay, 1 is, so u's length is 1, so it shouldn't be this long, but this long, okay, same length. If u, then if we multiply 1 by u, then the result is u itself. Okay, so indeed, the result is the rotation of 1 by the argument of u counterclockwise. Okay, so therefore 1 is rotated by argument of u counterclockwise. Clockwise. And next, step 2. Step 2. Now consider imaginary unit. Okay, and let z be any complex number. Then consider the product between these two. Okay, iz, which is, so ia plus I squared b, but I squared is -1, so we have -b plus ia. So this is the result. Let's plot this on the plane, real and imaginary. Let's say z is here, a plus ib, and let's say I is this. Okay, so if we multiply these two, this and this, then the result is this. Okay, so if this is b and this is a, then the results, the product's real part is -b. So let's say if negative is b is positive, then that will be somewhere here. -b is somewhere here, and a is somewhere here. So the result would be something like this. Okay, so this is -b plus ia. And now we show that this resulting point is the rotation of this vector, this complex number, by the right angle. That is pi over half, pi over 2, half pi. Okay, to show that, we use the Pythagorean theorem. Okay, remember Pythagorean theorem? So the square, so since this is, as we will see, this is the right angle. If this is the right angle, then we have the Pythagorean theorem. So the square of this length and the square of this length should be equal to, if we add them, then that should be equal to the square of this length. Okay, that's what we are going to show. And of course, the absolute value of this one, imaginary unit, is of course 1. Okay, so this is a special case of u we've been using. Well, anyway, so first of all, the length of this one, what is it? Is the absolute value of this. Okay, it's if squared, we have a squared plus b squared, right? And what's the length of this one? It's the absolute value of this one. So that is negative b plus ia. So it's modulus squared is, again, actually it's a squared plus b squared. Okay. So if we add them, we have 2a squared plus 2b squared. Now, what is the length of this edge of the triangle? Again, here we use the two-dimensional geometry. So this point is, the coordinate is AB, and this point, the coordinate is negative B and A. So the distance between these 2 points is given by, the distance between AB minus BA is given by this minus this is a plus b squared plus, and this minus this is b minus a squared. So if we calculate this, expand this, we have a squared plus 2ab plus b squared plus b squared minus 2ab plus a squared. So this and this will cancel. And we have a squared twice, b squared twice. So we have this. Now, this is equal to this. Therefore, we have this triangle with the right angle here around the origin. And actually also, this distance and this distance is the same. So this length, so wait a minute, this length and this length are the same. Okay. Also, when we calculated the distance between 2 points, this corresponds to the difference between 2 complex numbers, right? So a plus ib minus b plus ia is, so a plus b and plus ib minus a. So if we calculate the absolute value of this complex number, we have this. See, a plus b, and b minus a, b minus a. So the length of this edge corresponds to the absolute value of the difference between 2 complex numbers. So step 3. If z and w are any complex numbers, and u is, of course, again, a complex number with a magnitude of 1, then multiplying by u doesn't change the length of the difference, the length of this complex number. So this is equal to, so product, the absolute value of the product is the product of absolute values. So we have this, and because of this, we have ZW. Okay, so that means if we have 2 complex numbers, Z and W, then we take the difference between them. Okay, so in that case, that difference will be this. And if we multiply the complex number corresponding to this difference by u, then the resulting complex difference, so this will be u, z, and u, w, then the difference would be this. So this is some complex number. So this one, z, is transformed to this point, w is transformed to this point, but the difference, the distance between these 2 points doesn't change. So this length and this length, they are the same length, okay, as we can see from this calculation. Okay, finally step 4, which is a bit involved. For this, we consider the triple of three distances. Okay, let z be any complex number, and we consider the distances from 3 points to this point. Okay, first, the distance between z and 1, and the distance between z and the origin, 0, and the distance between z and I. Okay, we consider these triples. Okay, so if we determine a point, then we can calculate these 3 points. And conversely, if we specify 3 distances instead of a point, then there is only 1 point that satisfies this distance. That means, okay, so let's say we have a point here, and we consider the distance between this point from 1 and from I and from 0. Okay. Now let's say this is d1 and this is d0 and this is di. Okay. So the set of points that has the distance from 1, that is d equal to d1, is defined by the circle. Let's see, centered at 1, and so this is d1, and the radius of d1. So it's like something like this. It's the circle, something like this. So all the points on this circle has the distance from 1 that is equal to d1. Okay, d1. Now, the set of points that is separated from the origin by the distance of d0, this is d0, is defined by the circle centered at the origin with radius of d1, right? So we have something like this. Okay, so maybe we should use a different color. So let's blue here. So if we specify 2 distances, d1 and d0, then there are 2 points that satisfy that condition. Okay, this point and this point both have the distances from 1 and 0 that are equal to d1 and d0 respectively. However, if we specify another distance, di, then what happens? So the set of points that are separated from the point I by distance of di is defined by this circle centered at I. Okay, so all the points on this circle has the distance of di from the point I. So if we give these 3 distances at once, then the only point that satisfies that constraint is this point. Okay, no other points can satisfy these 3 constraints at once. So in this sense, 3 distances determines a point in the 2-dimensional space. Now, consider multiplying these points, z, 1, 0, I. So multiply all these numbers by u. Okay, then what would happen? So we have uz, and u times 1 is u, and u times 0 is 0, and u times I is ui. And then consider the distance corresponding to this. Okay, so z is transformed to this point, and 1 is transposed to this point, 0 doesn't change, and I is transform to this point. So the corresponding distances will be this, and uz minus 0 and uz minus I. Okay. And however, this is equal to, as we have seen, multiplying by u doesn't change the distance. So it is equal to z1 and z minus 0 and wait a minute, this is ui. So z minus I. Okay, so this is equal to this distance, this is equal to this distance, and this is equal to this distance. Okay, now u is a point that is obtained by rotating 1 by argument of u, as we have seen in step 1. Where is it? This one. So 1 times u is u. Okay. So by multiplying by u, okay, let's say this is 1. Then if we multiply by u, if u is this one, then it is rotated counterclockwise by argument of u. Okay, now ui. Okay, I is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I is here, and if we multiply I by u, then what we get is something like this. So IU will be somewhere here, and this angle corresponds to argument of u. So this is argument of u. So this angle and this angle, they are both argument of u. So both are rotated by the same angle. Okay, this angle and this angle. Now, if z is somewhere here, then z is also, by multiplication of u, rotated to somewhere. Okay, so by what angle is it rotated? That's the question. Okay, now as we have seen, if the distance from 3 points are given, then the point satisfying those distances is unique. There's only one point. So since from the beginning we know that z is the only point that has these distances from respective points, then if 1 and 1 and I and 0 are transformed in this way, then the only point that satisfies this distance constraint is the point that is obtained by rotating z by the same argument u. There are no other points that can satisfy these constraints. So in this way, we can see that multiplication by u rotates the point z by argument of u counterclockwise. So that is, everything is rotated by the same amount as long as u has the absolute value of 1. So we are done. So now let's go back to multiplication by any complex number. Let's say alpha is a complex number. So alpha times z can be written as this. So alpha absolute value, I'm assuming this is non-zero. Of course, if alpha is 0, then the result is 0. Okay, it shrinks to the origin. And we have this times z, right? And the absolute value of this one is 1. So first, by this multiplication, this z is rotated. Okay. And let's say this is z, and let's say this is alpha. So alpha divided by its absolute value is is a point somewhere on this arrow, but of length of 1. Okay. So if this is argument of alpha, by scaling, the argument doesn't change because the angle doesn't change, right? So this z is rotated by this angle, so maybe something like this. So that's what we have. Then we scale this arrow by this amount, absolute value of alpha. So that is this. So this length is the same as this length, and this length, this length is the same as the absolute value of z times the absolute value of alpha. Okay. So first rotate, then scale. Or either way, of course, we have commutativity of complex multiplication, so we could rather scale first, then rotate. So scale first, then rotate. Same thing. Okay, so that's all for this video. See you later.